Sorry, Riccardo.
Don't worry. Don't worry. By the way, in your swap operator, can you just swap A and B? Just apply it to A.
You can apply, if I give you A, you can apply A and B.
Said if you're lucky with one measurement, you get.
They're different.
Yeah, if you're lucky with
You'll find they're, but you won't know if it's A and B or B and B because they'll both give.
Ah, you know which is which.
Yeah,
sorry. But you can tell that they're different if you're lucky. Okay, so let's try to come back on Earth, where we know what we measure, we know who measures it. We may disagree on the systematics, but I mean, it's also good to have something certain. Capital D. So yesterday I was analyzing the structure of the extended standard model. This is to say, the standard model with all possible operators, as according to the interpretation of the standard models in effective theory, defined below some scale that it could be a constellation of scales. Okay, these lambdas that appear here do not have to be the same because we know that there is, in quantum field theory, already in the standard model below the weak scale, we see that there is various different energy scales. But overall, let me be very, very simplifying, and let's just put one scale and allow couplings. And what we and the concept, the idea was the point I was making yesterday is that if you take the first line, the line associated with operator of dimension 4, you see all the effects. Each and every one of those effects has been measured. Okay, and to various degrees of accuracy, some of them very, very good. And as soon as you go you plunge into the higher dimension things, you start encountering phenomena, effects that we either see very small or we don't see. And I discussed at length neutrino masses, and I was discussing what you get when you go to dimension 6. So most prominent effect that you get at dimension 6, if you allow all that can happen, you start having individual violation of individual lepton numbers in the charge sector. So you can have this integration of mu to E gamma. If you have complex coefficients, you can have electric dipole moment. And the electric dipole moment of an elementary particle, you should now be convinced, violates both parity and time reversal. Okay, violates Cp and T. And there are very, very strong experimental constraints on this effect. In fact, to date, we have not yet observed any EDM of the elementary particle, neither the electron nor the proton. The proton via the quarks, okay? And the constraints you get here, by normalizing the coefficient already being fair, normalize the coefficient with a suppression that is of the order of the mass of the associated fermion. This is simply because an operator like this, apart from the Lorentz structure, has exactly the same flavor structure of mass terms. It's like a mass term with two indices, with two Lorentz indices, and in line with the ideology of symmetry and selection rules, you would expect in the natural theory this coefficient to share the same suppression, and that is precisely what happens in all sensible constructions, okay, microscopic constructions of beyond the standard model. In fact, I don't know whether in string theory, when you generate Yukawas by worldsheet instantons, you also generate these effects. You probably should, right? These are d2 theta integrals, and they come with the same suppression. And again, you get not as big a scale, but you get a big scale. If you go then to things that are amazingly sensitive to new effects, like the KK bar mixing phenomenon, where you have both mixing and CP violation, then you get, under the assumption that you have no suppression, you get a huge scale, 10 to the 8 GeV. If you allow for some structure, for some suppression of this coefficient, the most hopeful suppression you can hope for is something of the order of the Yukawa coupling squared. Then again, you get some lambdas of order 10, 20 TeV. So it's still a big scale. And then you get this, you go forward, you get also another phenomenon that did not observe. You get proton decay. And there we know that the scale has to be bigger, 10 to the 15 GeV. Okay? So you get in this part of the Lagrangian, that is in the irrelevant operators, you get all things that we don't see, or things that it took very, very long to see, very, very small. So the nature seems to be telling us loud and clear that the standard model is an effective theory with a very, very high cutoff. The fundamental scale underlying the standard model is very, very large. Okay, so that's the. So what did you say?
Are there more really that you'll see that higher dimension also?
Oh, you could have neutron anti-neutron oscillations. You have delta B equal 2, but the bounds are weaker than from proton decay. It's a higher dimension operator. It's a dimension 9 operator. So you can get. There are other things. This is the only thing I can think of. Yes. Yeah, you can have that. I don't think anyone has analyzed more than this. I mean, of course, yeah. But I think pretty much here you have destroyed all the. In fact, I should say that in fact, this is the next transparency, the next blackboard. This success of the standard model is not by chance. You can view it in a more structural way as follows. The standard model at d equal 4, okay, has a set. So the this distinction between these two parts of the Lagrangian is that the d equal 4 Lagrangian, so the success of the standard model just at the level of d equal 4, is in one-to-one correspondence with the accidental symmetries enjoyed by d equal 4. Okay, the Lagrangian d equal 4 has just as by accident, if you want, baryon number symmetry, u1 lep1 cross u1 lep2 cross u1 lepton 3. So the three individual lepton numbers are preserved. It possesses some flavor symmetry, which I will specify in a moment. And it possesses another symmetry known as custodial symmetry. And this other symmetry, which I did not describe here, is a symmetry associated with the Higgs sector. And it is broken by an operator of dimension 6, which I can write here, h dagger d mu h square over lambda square. Okay. It's a property of the Lagrangian of dimension 4. Basically, the symmetry associated with this fact, the Higgs doublet is made of 4 real scalars. These 4 real scalars are embedded in an SU2 doublet, but 4 real scalars can also be embedded in O4. Okay, and as you know, O4 is SU2 cross SU2. Okay, now one of these SU2 in this O4 is the SU2, the gauge SU2, the electroweak group factor. Another group, the other group is not a symmetry. It would be, it's not gauged, but it happens to be an accidental symmetry of the d equal 4 Lagrangian. Okay, and this symmetry this accidental symmetry is only broken by tiny effects like the hypercharge couplings, or from loop effects like from the top sector. Okay, and this accidental symmetry is crucial to account for precision electroweak data. For instance, for the fact that the W and the Z mass are related to one another by a power of the cosine of the Weiberg angle. It's associated with that. And all this feature, that feature is lost as soon as you add an operator like this. Now, so the properties that, so the standard model at the d equal 4 level has by accident all the things that we observe in nature, baryon number, lepton numbers, and it has a violent set of selection rules as concerned flavor. Okay, in the standard model, there are 5 types of multiplets. Okay, there are the Qs, the doublet triplets, there are the up type SU2 singlet, there are the down type SU2 singlet, there are the lepton doublets and the lepton singlets. Okay, there are 5 types, and for each of these 5 types, you have three families. Okay, and at the level of the kinetic term, this Lagrangian has an SU3 to the 5th symmetry, okay, which is known as flavor symmetry, and this symmetry is broken in the d equal 4 Lagrangian only by Yukawas. Okay, so the only source of breaking of this symmetry at the d equal 4 level is constrained to be contained in 3 matrices: the Yukawa of the ups, of the downs, and the electrons. And this amount of breaking is very little. There's not much. Okay, in the sense that there are not very many sources of breaking. These sources are very special. Okay, they have very special quantum numbers under this symmetry. And the result of that, and on top of that, they have a structure. They have small entries. Okay, like the electron mass is small, the mu mass is also small, and the mixing angles in Kobayashi-Maskawa are smallish. But because of the selection rule of this SU3 to the 5th, all these smallish effects cooperate to make very, very small effects in physical observables. You get, for instance, in KK bar mixing, the effect I was discussing before, in the standard model, you get automatically a suppression that comes from a power of the charge mass squared divided by the W mass, and here you have the gain for the orders of magnitude for free easily, and then powers of the mixing angles. And in CP violation, since to have CP violation you need 3 families, you really get the product of all the mixing. So this flavor symmetry is truly essential, and I will illustrate in a moment. For instance, because of this flavor symmetry, the electric dipole moment of the electron in the standard model comes at 4 loops. You really have to toss in everything to get an effect, while in supersymmetry it comes at 1 loop. Okay, and all these effects that are so crucial and so empirically clear in the world we live, get destroyed immediately as soon as you step into here. So to answer your question, if you go to more things, you've already got rid of everything, basically, okay? So lepton number is gotten rid here in a nice way. In fact, lepton number, we know it's all in approximate symmetry. It's very, very good, but it's only broken by neutrino masses, and that's it. Neutrino masses are a higher order effect. This is why they're so small. But all other effects that come from here are in particular proton decay, are immediately, so the symmetry gets eliminated right away as soon as you go to dimension 6. So the the comment that I make here is that is an invitation, is a I don't know how to say it. Well, I don't know how to say is a very strong suggestion. If I want to be bombastic, I say from nature. This is really telling us, look, it's very high. Okay.
You didn't mention G minus 2, did you?
Yeah, G minus 2 is in this category here. So you could have anomalous effects in G minus 2 from this part here. They're less constraining. It's more robust because it's always there, but it's less constraining.
In terms of the smallest possible scale for G minus 2, according to what scale?
You mean G minus 2?
The fact that there's this 2 sigma, 3 sigma effect there.
It's, I mean, G minus 2 of the muon, you're saying. I think it's 10 TeV. 10 TeV. I think it's of the order of 1 loop effect in supersymmetry. Here I didn't put loop effects, so you add a factor of 10. So, but it's compatible with supersymmetry at 1 TeV. So it's not. But anyway, it's not. It's true. You may say this. It seems to suggest that there is new physics, but there are certain. I don't think it's fair to invoke that to say that there is new physics. There are people that include that in standard model fits. In fits of new physics, like just to show that the standard model is ruled out. But I mean, the QCD uncertainties are. I don't know if lattice people could measure light by light scattering on the lattice one day. Because there's the contribution, and that is. Okay, so however, so this is what the point of view you get on nature, okay, when you look down, okay, when you look down here. When you look up, you get a different perspective, okay? When you look up, you go to dimension 2, and you realize that you had forgotten an operator, okay? This operator is the Higgs mass. Okay, and that operator is a relevant operator. Okay, and you're like in a seesaw. You would expect that according to naturalness, and I will say this better in a moment. Natural. You would expect MH squared to be proportional to this very cutoff scale just by times some coefficient to be discussed, okay? But we'll discuss in a moment. But you really see that when these guys go down, the other go up. It's like a seesaw, right? And it seems that there is no free lunch, okay? And you may want to elaborate precisely with the Higgs mass, precisely as we elaborated here. Here we derive some lower bound on the scale lambda. In the case of the Higgs, you can derive an upper bound. The upper bound is based on the notion of naturalness, which I illustrated yesterday, but is very much the same argument. A civilization that has observed the pion, it has seen that the pion has electromagnetic interaction, it has seen that the pion has a small mass, and that civilization predicts that there should exist new physics at 1 GeV. Okay, let me remind you again: the pion is below 1 GeV, is a scalar. The pi plus. Let me focus on the pi plus. And the pi plus is a charged scalar. Okay, it has a kinetic term, d mu minus I a mu pi plus squared. Let me put E here. And if it wasn't for the electromagnetic interaction, the scalar would be endowed with a shift symmetry. And compatibly with the selection rule of the shift symmetry, this scalar could be a Goldstone boson, as we know, in fact, is approximately is a pseudo Goldstone boson. However, you say, well, this parameter breaks the symmetry, so the pion mass cannot be naturally zero. And what do we expect for the pi plus mass? In fact, there's going to be a correction to the pi plus mass that will be of the order of the whatever fundamental scale there is. Every Lagrangian is effective, so there's some fundamental scale, time the parameter that breaks the shift symmetry. In this case is E. Well, E to minus E is not something that you can observe, so this should be quadratic in E. Okay, you can also exchange the sign of the, so it should be quadratic. And in fact, you can get a better hunch by doing a back of the envelope estimate of the pion mass from these diagrams, and you get that the correction goes like E squared over 16 pi squared times some integral that is formally divergent because just by dimensional analysis, okay. And but you know that there is no divergence, okay. The theory is effective, and this thing just indicates that this quantity here must be put equal to the biggest possible parameter, dimensionful parameter you have in your system. That is the cutoff. You do this estimate. You measure the pion mass. In particular, what you measure is the difference between the pi plus and the pi zero mass. The difference is 3 MeV. And from this difference, you infer what the value of lambda is, and you roughly get lambda of order 1 GeV. Bingo. This is very good. Okay. And this does not happen only for the pion. If you go back and think of the discovery of the charm, was exactly the same. There was an effective theory. In this effective theory, there was a formal. In this formal theory, you could compute the correction to a certain observable, which is the K0 bar mixing mass. You do the computation in the effective theory. This computation is formally quadratically divergent, like that. And now you ask yourself, well, I observed this mass difference. The question is, what is the scale lambda in this process that I should input in order to get a sensible result, a sensible order of magnitude? You look at what the scale is, and you say, well, there should be some new physics at the scale. That scale was about 1,2 GeV. This is how people were expecting to see the charm or something at that scale. And please.
Historically, did people also do for the pion mass?
No, this is the history. No, I don't think so. Sorry, probably Pierre can tell us whether the issue of naturalness was ever discussed historically for the pion mass. When Dacian no, there was no yet. But the prediction of the charm could have been inferred on naturalness argument. But particular, if people see in the let me tell you so the issue is the following: you have the Fermi-Cabibbo interaction. I say Cabibbo because there is flavor mixing. Okay, there is ds and there is u and u bar, ds bar like this. Okay, and this interaction is of order G Fermi. Okay, and now you close this loop. G Fermi time sine theta Cabibbo cosine theta Cabibbo. Okay, and now you close this loop. You get this vertex twice, and the loop running here is two fermion lines, 1 over p square, double integral, you get dp square. You get a quadratic divergent thing. And then this gives a four Fermi interaction involving d bar s. Okay, and this contributes to KK bar mixing. And if you just replace this integral here with the cutoff scale, you find that the experimental measured value of this transition matrix element suggests that this lambda should be of order 1, 2 GeV. And that at the time was a problem, and the problem was solved by Glashow, Iliopoulos, and Maiani. they modified the theory, they added a new particle, the charm. Okay, the mass of the charm is of order 1 GeV, and the presence of the charm is precisely what softens this apparently quadratic divergence. In other words, the role of lambda is played by the charm mass. In the theory with the charm, this effect is calculable and it is saturated at the charm mass. This is how the charm was predicted. If like people that think, oh no, you only have to compute in dimensional regularization, and done the computation in dimensional regularization, they would have gotten 0, and then they would have said, well, there's no problem. They would have missed the opportunity to get a Nobel Prize. Okay. Anyway, even Glacio-Posman did not get the Nobel Prize. It's only Glacio. But I think that was a great piece of physics. Okay. Probably that is the piece of physics that created what I've been doing all my life without finding anything. So that's it was great for them. It was okay. So now, if you play the same game for the Higgs, you have the analog of this diagram for the Higgs. There are 3 dominant guys. There is this guy here with the top. There is this guy here with the W's and Z's. And there is this guy here with the Higgs itself. And now we have measured the Higgs mass. We know what it is, 125 GeV, very much like we had measured here the pion mass. And by computing, squiggling precisely the same way these diagrams, we can tell where our analog of the QCD scale, or in that case, the analog of the charm scale is. And what a deduction you make is that the top sectors tell you that the scale should be below roughly 500 GeV. The W is telling you that it should be roughly below 1 TeV. And this one itself, the Higgs with itself, is telling you that it should be below something like 1.5 TeV. So roughly, the line D equal 2, unlike everything else in yellow, let me write it in yellow as well, it's giving us a completely different statement. D equal 2 is telling us that lambda should be below order 1 TeV. Okay, so these are the two contradicting statements, okay, that we get from this. So let me write it here. MH naturalness instead implies lambda less than order 1 TeV. So 1 and 2 are clearly contradicting each other. And the contradiction is stark because 1 is so nice. It's so convincing, this argument, okay, to really explain the structure, the very structure of the interactions that we see or that we don't see, just by taking one parameter and putting it larger and say all these effects are just higher multiples. Okay, this is why we don't see them. This you can really explain to an audience of engineers. They will be happy, I think. No, just multiple. I mean, radio amateurs. You're an engineer. Well, okay, good. But I'm not saying engineers in the sense that, I'm teaching at an engineering school, so I mean, I cannot joke too much about this, okay? And on the other hand, this conceptual, the very notion of dimensional analysis, and selection rules, that is the basic notion that guides us in physics, contradicts that, okay? So this is already a sort of a paradox. But you may say, well, okay, come on. What can you do? You could perhaps modify. Okay, for instance, let's take 2. Let's say that we want to act on 2. So we can't stand 2. We want to solve it. So what do we have to do to solve 2? Well, what we have to do is, see, it's 1 TeV here. In order to get rid of this embarrassment, we should modify. Okay, we should modify the standard model right around the weak scale, say around 1 TeV or less, okay? And so, okay, let's modify it. And modify it into a new structure, into a new theory, okay, where there are no embarrassment with strongly relevant operators not protected by any symmetry. Remember, we should extend the standard model to eliminate embarrassment 2 into a theory where the hierarchy is natural either because of marginality, because in this new theory there are no relevant operators or strongly relevant operators, or because of symmetry. In other words, that the only relevant operators we have can be protected by symmetries. Okay, and these two options are precisely correspond to the two basic ideas we have been thinking with, well, okay, probably decreasing amount of conviction over the last 35 years. They are compositeness and supersymmetry. Okay, and now here really lies the paradox, and you can see it right away. These two, in principle, beautiful and compelling solutions always necessarily destroy this very delicate property of the standard model. So in other words, there's really no free lunch. If you want to solve 2, you screw up 1. And that is really the essence of the hierarchy problem. Okay? The hierarchy problem cannot be just presented in terms of... you notice that I didn't even talk about Planck. Okay? There's not even need to talk about the separation between Planck and the weak scale. I stay very far away from gravity. Because now I learned to be far away from it. So I didn't even need to use that. I mean, the standard model itself intrinsically, and the notion of Wilsonian theories, namely effective field theories, is pointing to us a contradiction. Okay, so it's not a problem; it's the paradox. Okay, there's no way to do good in all ways, and let me explain why. Take, for instance, let me explain why. Let me give you an illustration of why, if you try to solve this problem or define the standard model, why you screw up this. And let me give you the two standard examples. Okay, let me start with the first class of solution, which is solution of the hierarchy by marginality. That is what normally goes under the name of Technicolor, conformal Technicolor, Randall-Sundrum, compositeness. Simply amounts at the assumption that the Higgs is truly is not an elementary degree of freedom, okay, but it's a composite bound state, very much like the pion is, and the scale that appears here is roughly compositeness. Okay. Notice that in the original version of Technicolor, there was no light Higgs. The theory was a strong coupling, okay, and the Higgs was like a sigma, was like a broad resonance. In the modern versions of Technicolor, which are now called composite Higgs, just to identify the community that is working on these things, posits that the Higgs is a Goldstone boson, a pseudo-Goldstone boson of some global symmetry. And there are varieties of models of this. Okay? But let me tell you immediately a basic structural property that you see different between the standard model and this theory. So the essence of compositeness of Technicolor is that the Higgs, let's say Technicolor, the truly beautiful Technicolor of 1979, okay? Was beautiful in 1979, as Joe said. So the Higgs, okay, the Higgs, where alpha is the SU2 quantum numbers, gets promoted to a fermion anti-fermion condensate, okay, where I are the Technicolor indices. Okay, so the Higgs gets promoted to this thing. So again, in the theory above 1 TeV, in the theory above the weak scale, again we have the typical paradigm that I discussed before. We have an approximately conformal theory, well, approximately free, and in this theory, this operator has dimension 3, right? It's a psi bar psi 2 fermion. Okay, it has about dimension 3. And now look at what happens for Yukawa couplings. And let me call it better, L flavor. So the Yukawa couplings now are irrelevant. Okay, before they were marginal. Now they are irrelevant. They are pushed down in the area of the things that we don't see. So we have the Yukawa couplings. Okay, the Yukawa couplings are like T bar T, psi bar psi. with some Yij, whatever, divided by whatever ultraviolet scale we have. And this is what we see. We see. And then, exactly at the same level, we have Kij, Kl over lambda square, psi bar I, psi j, psi bar k, psi l. We do not see. Okay? It's just as simple as that. Before, between what we see and what we don't see, there was a genuine structural separation, operators of this different dimensionality. I push the cutoff high, all this junk goes away, is irrelevant, and all is left is some purified water. Capipo Kobayashi Mascavo flavor theory. Here, if I try to get rid of this, I get rid of that, and if I want this, I have that. Okay, so and that's the basic difficulty of compositeness. Okay, and over these last 35 years, we've made careers to try to solve this. Okay, we don't really have a nice solution. Okay. And flavor remains the major obstacle. I mean, we have clever ideas, but this cleverness, compared to the coolness of the standard model, does not match in flavor. Okay, as far as flavor. Of course, this theory solves the hierarchy problem. Okay, the hierarchy. There's no in this theory. There's no relevant operator associated with the Higgs. In fact, in Technicolor, if you want, in Technicolor, the analog of the H-dagger-H operator is the T bar T squared operator, which has dimension 6, right? So it has dimension 6, so it's irrelevant. So what before was a curse now is, okay? In fact, what generates the scale now is no longer the Higgs operator, but it is the Techni-gluon kinetic term that, very much like in QCD, is marginally relevant, and you have the analog of QCD. Okay. Now, there have been attempts to address this, starting from the 80s, based on the following idea. Okay. At that time, it was still not well framed, but it was there. Okay. And the idea was basically that what if Technicolor above the weak scale, rather than be described by a approximately free conformal field theory, is described by an interacting conformal field theory. Okay. Now, in that case, the dimension of the associated operator does not have to be 3; it can be lower. Okay. And this is the idea first put forward by Bob Oldham, known as walking Technicolor. Okay. Of course, this idea was put forward. I don't know why, but it was not put forward in the modern, I should say, in the 70s, because Polyakov, Ferrara, Gatto, Grillo already had done all their work, a language of conformal field theories. Okay, and I think because of this fact, it led to a huge confusion that in some pockets of my community still persist. Okay, how it's phrased and how it's, but you can really state it very simply. Okay, let's assume that above the weak scale, the Higgs sector is embedded is part of a non-trivial interacting conformal field theory, and in this conformal field theory, there is a composite operator. Let me call it T bar. Let me call it H. Okay, H is composite, and H has dimension D of H. Okay, where D of H is, let's say, D of H is to be bigger than 1 because of well, bigger or equal than 1 because of unitarity. Okay, and it can be whatever you want, but let me say 3. This corresponds to Technicolor. This corresponds to the standard model. Okay, but it looks like between the standard model that is problematic and Technicolor, there is a small prairie, okay, of between 1 to 3, where you could have something interesting going on. Okay, and that is the reasoning that, for instance, was put in modern days in a more framed way by Luti and Okui, okay, with the idea of conformal Technicolor. And this framing, this intelligent framing of the question, okay, which I'm going to make, is what suggested it was stimulated the revival of the bootstrap methodology. Okay, let me give you how you. Let me sketch you very quickly how would you argue this way. Okay, so let's imagine H. I'm already late. Okay, let's imagine. Let me go very quickly. Let's imagine H as dimension dH. So now this operator here is as here you have dH minus 1. Okay, you agree with me? Okay, to get the dimension, this is dimension dH. Okay, tac tac 1. This is dimension 4. Okay, and it's clear if now dH is less than 3, dH less than 3, then this is more important than that. So we start selecting what we see from what we don't see. Okay, the question is now a quantitative question: how much you want to select this? How much you need to select it? Okay. Well, let me tell you very quickly. Okay. Look, this operator is irrelevant. Okay, you see it is irrelevant. We have measured. So this is in fact a matrix. There is everything. There's the electron mass, the mass, but in particular there's the top Yukawa here. So an irrelevant operator is an operator that if you measure at one scale, at a higher scale, it has bigger effects. So the top Yukawa is already order 1 at the weak scale. Okay, so this will tell you that the effective top Yukawa, lambda t running at scale q, will go like I'm neglecting factors of pi's and stuff like that. It will go like y top at the weak scale. Okay, lambda weak m top times the q scale, the normalization scale over the weak scale to dH minus 1. Okay, an operator of this dimensionality, the running coupling grows like a power. And you see that if dH is not sufficiently close to 1, okay, the top Yukawa blows up, okay, right away, and you get a theory, you get a very low cutoff, okay, and again, you're back to a theory with a very low cutoff where you don't have a separation of scales. What you would like to have is a situation where the coupling remains small until some scale sufficiently high to suppress all this other stuff. Okay, and now so the top Yukawa, and in particular top Yukawa. So if I can now start drawing dH here, and here you have 1, here you have 3. This Technicolor. Here you have 2. Here you have 1.5. Oh, I didn't draw it well. Let me write 1.5 here. Let me write 2 here. And 3 goes out of the window. Okay? And so the top Yukawa would like you to be in this area here. Okay? We like D to be less than roughly 1.5, even less. Okay? And similar constraints are coming from flavor physics. Okay? Because you want. Well, it's complicated to say, but let me just to simplify the argument to talk about the top Yukawa. There's no need to talk about 2 things. But now, as you know very well from conformal field theory, when the dimension of an operator tends to 1, the operator becomes free. Okay, it decouples from the conformal field theory, and its matrix element factorized, and in particular, its OPE becomes in a sense trivial. It's the operator square will have roughly dimension twice the dimension of the operator. Okay, when dH goes to 1, there will be in the OPE, well, the dimension. I can define an operator h decker h. Okay, h decker h is defined as the lowest. Is defined like this: lowest dimension scalar in OPE h with itself. Okay. In the standard model, in a free field theory, this guy has dimension 2, but in the conformal field theory, it can have any other dimensionality. Now, we don't want this guy to have dimension less than 4. If this guy has dimension less than 4, we are back to the hierarchy problem because there is a very relevant operator. So we want the dimension I write it here. This is 4. This is the dimension of h dagger h. We want the dimension of this guy to be close here. So basically, the top pushes here, naturalness pushes there. We want to be in this region here. Okay, roughly 1 to billion area here. And the question is, how much of this area is available by prime principles? Okay, and the bootstrap allows you to explore this question and answer to it. The bootstrap allows you to give an upper bound on the dimension of this guy. Okay, it gives you an upper bound on the dimension of this guy, and you get a plot that goes like this, roughly. You may have seen it in the talk by Simons-Duffin. This guy crosses 1.5 and 4 roughly here. So you have to be here. Okay. So it seems like the dream of having a beautiful situation where you have, let's say, the h dagger h as dimension, say 1.2. I mean, h dimension 1.2 and h dagger h dimension 4. Which perhaps could have happened, right? You have factors of a few. I mean, dimensional analysis, you get factors. Doesn't work, okay? That doesn't mean that the idea is completely to be thrown away, okay? With some additional assumption, you can extend this area here. But again, you need additional assumption, okay? You always, in phenomenology, model building, you measure the plausibility of what you're doing, but the assumptions you put in, okay? And perhaps this is not the right criterion, but this is all we have, okay? And so it looks like the problem of the possibility of filtering what we see, what we don't see, does not work just because of the intrinsic properties of conformal quantum field theories in 4 dimensions. So that's the first difficulty. And this is why, for instance, in composite Higgs models, now we think of the origin of fermion masses in a different way. Rather than having the standard model quarks coupled to a Higgs operator, we have them mix to composite fermions of the Higgs sector. It's something different that I wanted to describe, but I will not have time to. Okay, but again, that also has some price. This is what concerns Technicolor-like theories. Let me go to the other side, to the other half of the sky, that is supersymmetry. Okay. Now here, it's very simple. The Higgs mass in the minimal supersymmetric standard model, which I will describe in a moment, well, in a moment, today and tomorrow, if the time I have, is protected by supersymmetry plus chiral symmetry. So basically, in the supersymmetric standard model, the Higgs mass becomes like a fermion mass. There's a chiral symmetry under which it transforms, and you can assign selection rules to the Higgs mass while keeping its interaction intact. The beautiful thing about supersymmetry is that allows you to have scalars that have sizable interactions while still having selection rules for their masses. Okay, so this is the way supersymmetry works. However, the problem of supersymmetry is now to make it into a real theory of nature for the standard model, you have to double the spectrum, and now you will have to add partners, bosonic, scalar partners for all the standard model matter, okay, for the quarks and the leptons, okay, and it's just a fact that scalars have dimension 1 in weakly coupled theories. The standard model is weakly coupled, so we extend it, it's still weakly coupled. So all these partners of the quarks of the standard model will be scalars of dimension close to 1. And now you see how things can be different. You see, one crucial feature of the standard model, why all this junk was higher dimensional, is that fermions have dimension 3/2. Okay? If you put together 4 fermions, 3/2, 3/2, 3/2, you become irrelevant. But if you put together 4 scalars in all possible crazy ways, okay, you get to dimension 4. You get marginal operators. Okay, so for instance, in supersymmetry, you have the quarks, okay, and the leptons, the quarks and the leptons, and right away you can write things like U tilde. It's UU, it's UDD. No, it's UUD. E. So you have an operator with four scalars that you can contract color here. These are colored objects. This makes a color singlet. It's a baryon. It's a scalar baryon. This is a lepton. Okay, charge is conserved. This is a marginal operator, precisely of the type that induces proton decay. Of course, the proton is not a boson. You have to dress it up with the typical interaction of SUSY to turn it into a transition for fermions, but that can be done by marginal interactions, the marginal interaction of the MSSM. So this guy right away makes proton decay, something that we don't want to see, something which, just by dimension analysis, comes in at the same order than the things we see. Okay? This is one thing. And of course, this can be, again, this requires model building. Need extra assumptions. Extra assumption means model building, means R parity. R parity is sufficient to eliminate this. You also have so quarks have dimension 1. So you can have even relevant operators, Mij, which mediate quark mixings. Okay, so in general, this guy here, Mij squared, has nothing to do with the CKM, with the Yukawa matrix, U and D. So when you diagonalize one, the other is not diagonal. So there will be additional sources of flavor violation in this matrix. And this is a relevant operator, dimension 2, something that you don't have in the standard model. And again, you have to come up with ideas on how to set up the microphysics of your supersymmetric model, something that you did not need there, in order for this term not to be damaging. Okay? So this is one favorite idea, is that the soft term, these masses of scalars are generated by gauge interactions. Okay, and since gauge interactions are the same for all flavors, these guys are proportional to an identity matrix. Delta ij, okay, and the identity matrix has the property to be the identity in all frames, right? So off-diagonal entries are 0 in any frame. There's no flavor mixing. Again, this requires model building ingenuity. Okay, something that in the standard model comes for free. Here comes at the price. And there's really something. I mean, it looks like nature is telling us something, but we don't know. So this is not to say that we don't have models that work. Okay, we have models that can make it work, but there is a difference. Okay, there's a difference compared to the standard model in all these features. And in my opinion, this is the essence of the hierarchy problem. This is also the reason why we may not be surprised if we don't see anything at the LHC. Okay, it may be that all this issue of the naturalness is not the right way to pose the question. As you know, as you've heard, I don't know how much Nima is still going around saying these things. There is an alternative point of view that states that perhaps this issue about the structure of the parameters is not decoupled from historical things, right? The history of the universe, okay? And so this is the explanation that goes through the landscape. There is a vast landscape of possibilities for the Higgs mass, okay? And it happens to be what it is without apparent stark violation of selection rules, simply because there are so many possibilities that this possibility exists, and it turns out that this possibility seems to be the only one, the one where the standard model has this structure and the Higgs is just fine-tuned, seem to be the one that is not only consistent with these nice features, okay, with the data, but also so the reason why the Higgs mass is what it is could be associated with the fact that if you change a little bit, okay, it turns out that the structure of the universe changes dramatically. So issues like complexity disappear. So for instance, if you take the Higgs mass and you increase it by a factor of 5, without changing any other parameters, the Higgs wave increases by a factor of 5, the quark mass is increased by a factor of 5. It turns out that now the mass of nuclei is very much affected by the value of the quark masses, and in particular the up quark mass is the lightest, okay, and the down quark mass is slightly heavier. So the quark mass wins in importance in nuclear physics compared to binding energy, okay? And the net result of this is that basically the only stable nucleus is a nucleus made of 3 up quarks that has the same charge as a helium nucleus, okay? And that's all there is of nuclear physics. Just enough to change the Higgs wave by a factor of 5. So perhaps these accents are not there by chance, and perhaps the whole picture is the whole picture of naturalness is not relevant to this question. And it could be. Yeah, of course. That's the problem of the landscape. You can increase it, then decrease the Yukawas, and then right.
Something about the gene. You talked about the gene mechanism. Before the gene mechanism,
long ago, yeah.
it was basically a puzzle, like certain processes, with no implication of landscape or anything else.
Sure.
There was just something itself. Then with the gene mechanism,
And it worked within a year.
by adding one.
Yeah, it worked within a year, right? Yeah. Now,
Before, I mean, in the early 60s, I'm told, the problem was already there.
in 64. Earlier, you mean before CP violation, you mean? When there was just KK bar mixing.
People knew,
Yeah,
apparently, according to the pioneers, that there was a problem. Nobody knew.
Okay.
By adding one part.
But they found it right away, right? Yeah.
Yeah, of course.
No, but these issues were no, I mean, no issues like the real pros for fine tuning. I'm not sure they were there. Here there are some pros for a fine tuned theory. Yeah, perhaps if people had formalized, they would have found the pros for a different yeah. But I'm not sure they would have. I mean, this structure standard. I mean, is pretty clever, right? I mean, I've been doing model building all my life, and so I don't. It's an empty statement saying that this is the reason why I'm aware of this problem. But anyway, it's not done. There are problems in increasing gravity as you go, in all senses, as you go to dimension 0. Okay, and there is this guy here. Okay, and okay, this is just to close the discussion. Okay, and there is another guy here in decreasing gravity. Okay, but we know the action exists. Okay, and they will discover it. I have no doubt. No doubt. I'm willing to bet. They will find the action. I mean, there's no anthropics for this. I mean. Did anyone try? Since you were around the Stanford, did you try any anthropics on this? And?
There's a paper by Hertzberg and Wilczek.
Yeah. And? Yes, you're right.
Windows. Yeah, I think yeah.
It's a window. I hope they didn't jump from. Okay. It's a window. Okay. I think now I have two options now. I could go on and tell you more about these features, special features of the standard model, why the very structured standard model is such that, for instance, the EDM of the neutron, of the electron in the standard model comes at 4 loops. It comes from a loop like this, okay? There's a loop. I think this is the loop, but it's something like you have to attach a photon. Of course, you have to have the 3 family of quarks going through, so you have something like this. Here allows to have all the 3 families, otherwise you don't see CP violation. But CP violation in the standard model is all in the quark sector. So to feed to the electron sector, then the electron has to couple to them with the W. So this is the thing. So this you get 10 to the minus 38. Okay? Then you get 10 to the minus 38 e times centimeter. The experimental bound, the experimental is less than 10 to the minus 28. Okay? In supersymmetry, this is the standard model. In supersymmetry, I think Joe is one of the first to point this out. I think he did it because it's simple. Okay, it's just one loop. You can do it. Sorry, you can do it this way. Well, there is. Well, okay. Look, there is like a gaugino here. There is the left-handed and right-handed selectrons, and then you touch the photon wherever you want. You can touch it here. This is E, and there is E. And so this diagram is a one-loop diagram, and you get a contribution that is basically the SUSY. Let me just improvise. Is the phase? There's some phase phi, which is a phase of your couplings. I mean, CP violation comes from the complexity of your couplings. Phase CP times the experimental bound times order 3TV over M SUSY squared. Okay, so you get at one loop something that with SUSY at if there is no small CP phase, SUSY, the relevant particles are way out of the LHC reach. These are particles without color, so you never see them according to this. This is very, very important. The fact that we don't see anything is not so shocking. Okay, but okay. Of course, we all have constructed model where this phase is small. Okay, I have. Okay, and you can. Okay, but we are clever. Okay. Okay, so I think I can clean. I have 10 minutes, so 10 minutes, 10, 15 minutes. And if anyone has comments, I can try to answer. Otherwise, I do the squeegee in silence. So, I mean, Pierre, what did you say? You meant that I'm overselling this niceness of the standard model?
I don't like the landscape.
It's not a question of liking things. Like we are scientists. I mean, why? Why you don't like it? Because you say it's like giving up. But by the way. Yeah, but the landscape is a much more dramatic discovery, right? In a sense, it's very interesting because it's so revolutionary. It's the ultimate Copernican revolution. Before the Earth was the center of everything, then the sun became the center, then the galaxy, then the universe, and now the universe is this lives in a banlieue, as the French would say, of a much bigger thing. I mean, it's mesmerizing. I mean, it's truly.
It's a silly question. How do we ever discover?
That's a good question for a string theorist. This is the opportunity. You see, I don't know, but
It's a question for you.
yeah. So a few years ago, I can only report on something like this, and the paper never came out. But the author of this idea was very excited. Guess who he was? Okay. No, Nima. And the idea was that in this proliferation of universes, you can have universes that contain some charges, and then somehow these universes shrink because they are energy. I mean, they have by energy consideration of energy density inside and outside, they shrink, but they cannot shrink to zero because there's a charge that is conserved inside. So because of this, he was arguing you would have to have a continuum of exotic particles with varying mass and charge. So that is basically, that's the gist of the idea. I cannot tell you that I fully understand it because I haven't done the details, but that would be an option. That an option that was presented, it was, the author of this idea was very excited, but then he probably got excited by something else, okay? Because the paper was never written. I don't know if anyone heard. You should ask Nima if you happen to meet him, ask him whatever. Can you create baby universes? I don't know. Takes big effort. No, I'm not sure we have. Can we see can we have a look? It's like evolution. How are we well, sure that evolution took place? We look first at the fossil data, and then we look at the variety of animals we see, and we have lots and lots of data. In the standard model,
How do we decide which questions are anthropic and which aren't?
I don't know, but I'm saying that if we had lots and lots of data, we could start seeing that we live always at the boundary of things. And Larry Hall has been playing this game in the last 10 years, and according to him, he has seen all possible ways in which the parameters of the standard model live at the edges, okay? They all live dangerously. I don't know. Look, let me give you something very dangerous, okay? As you know, the proton is slightly lighter than the neutron, okay? That's very good, okay? But as you know, the proton has charge. So you would think to put this charge together at a bound state would cost more than put together more neutral things. So you would expect that electromagnetism, so if you start from a situation where N and P are degenerate, which is what you have in QCD, pure QCD without quark masses, without electromagnetism, when you turn on electromagnetism, you would have a situation like this, by which hydrogen atom is gone. Okay, think of, instead of water, you have heavy water. Yeah, it's different. Okay, and and even nucleosynthesis changes dramatically. Everything will be very different in this case because of electromagnetism. But it turns out that M up is less than M down. And it turns out that the contribution of the quark mass to the proton and the neutron mass is comparable to the electromagnetic one in such a way that you get the opposite. So you get comparable contribution from different physics and crucial for the existence of complex things. So you change a little bit the Yukawas, this is gone. Okay, so we live at the edge there as well. I don't know. Look, I don't know.
Isn't that good? Don't you want to live at the edge where things boring?
No, I'm not saying that. So the question is what I can do. No, so my comment is not about I don't like this. What can I do about this? It's very hard to do physics, but sure. No, in fact, it's look. Testing directly naturalness remains very, very important, and we are not that much into the area where naturalness is tested. Okay, I'm not so shocked that LHC has not seen anything, because at least in the simplest model, because the models were already constrained for other reasons, flavor, and for instance, take composite models. Take the most recent, the most you use the best set of assumptions to get to tame flavor issues in the compositics model. There's always going to be a contribution to KK-bar mixing coming from the fact that the top is heavier than everything else, that the top will always mix more. Okay? This contribution cannot be eliminated by any symmetry. Basically, because intrinsically, the flavor matrix has only an SU2 symmetry because the top Yukawa is large. Okay? So this effect cannot be eliminated, and by this effect, you expect the masses of the top partners to be more in the 2 to 1.52, be very optimistic, range, TV. So a range that is natural, okay? It's not completely natural for the Higgs, okay? The amount of naturalness is, if you want to measure, given that you are talking about square masses, the square masses, it should have been 500 GeV squared, it's 2 TeV squared, there's a factor of 4 square, is a few percent tuning, okay? Okay, it could happen. But now, in the next run, we get into that realm. So this is why I'm excited. For instance, as I told you, I know this is a joke that I should say in this discussion. I bet a 1-star restaurant with Slava Richkov, dinner, that we will discover new physics in 1 year. Yeah, and then I bet 3-star with Peskin that we'll not discover anything in 5 years. Okay, but that's to give you my feeling, okay? But that's like, perhaps I'll be dead by that time, so I will not have to pay anything to Peskin, okay? But in the short range, I want to. So this is just to give you an idea. Okay, I think I can start talking about supersymmetry, given that you guys are all stringers. You like non-perturbative effects in supersymmetry, all that stuff. I'll try to catch your attention with this. It's a desperate attempt, but let me do it. So supersymmetry, okay? So the idea was to outline the two major systems in the Galilei way that, well, there are three. Nothing, this is the standard model, supersymmetry and compositeness, okay? There are three major systems, okay? And I am Simplicio. I'm working on supersymmetry and compositeness, okay? That's very clear. So first thing, we know chiral fermions exist. So how do I construct the supersymmetry? So in this lecture and the next, now I'm almost done, I'll try to give you a quick view of the supersymmetric standard model and supersymmetry breaking, okay? In a way that is slightly different than the way it's presented normally, okay? That's the way people got to in the 80s. This is slightly different, and I think it's more in line with our present view of things, okay? So supersymmetry. First of all, chiral fermions exist. How we construct the model, then we know that it must be n equal 1. So I'm sorry for all those who work on n equal 2, n equal 4, just n equal 1, okay? Just, it's great to have all these other things, but really for the bread and butter particle physics, it's okay, n equal 1. And then how do I construct the multiplets? One question that you may ask is, how are gauge symmetries embedded? Could gauge symmetry, for instance, not commute with the supersymmetry? Of course, if the gauge group does not commute with supersymmetry, the supersymmetry becomes immediately non-local. Okay, so you local. Sorry, so you are in gravity. But in fact, you can, and this causes some set of complications. But let me cut it short very quickly. In n equal 1, the only gauge symmetry that can not commute with supersymmetry is a U1R, okay? And it's just a theorem of supergravity that a gauge U1R is either broken at the Planck scale or supersymmetry is broken at the Planck scale. Neither of these situations is of interest, okay? So the only U1R we have in the standard model, the hypercharge, cannot be a U1R, okay? So therefore, the gauge group should commute with supersymmetry. And so the multiplets that we are interested in should be multiplets of states with the same gauge quantum numbers, but different spin, okay? And the other thing is whether, and as you know very well how the thing is constructed, you have okay, so matter is constructed in the following way. There are the lepton chiral multiplets, which involve the left-handed doublets and their scalar partners. Let me eliminate the indices. These all go from 1 to 3. They have 3 families. So this is the left-handed doublet. There is a left-handed lepton and a left-handed slepton. And then there are the E's. Okay, these are the right-handed singlet in the standard model is just a Weil spinner. And then there is their scalar partners. And then at the level of quarks, you have the quark doublets and the quark doublets, and then you have the U's, the up-type right-handed, the up-type singlets. In fact, this should be anti guys, right? They should be anti-electron, anti-quark, and I will drop this C all the time, okay? Just because I'm lazy. And then there is the DC, and DC twiddle. So this is all there is in matter. Higgs, the Higgs must be also embedded into a chiral multiplet, and it cannot be embedded in a gauge multiplet for the reason I told you. Okay, it's a doublet, and in the gauge multiplet I will have other quantum numbers, so it will also be embedded into a chiral multiplet. And it turns out that because of anomaly cancellation, if you only have one Higgs doublet, you only have one single chiral partner, and this would have, first of all, a global Witten anomaly, but also ordinary anomalies. Okay, so you have to double the Higgs spectrum into H1, that is called the Higgs doublet H1, and its own partner, the Xeno, and H2, that is a Higgs doublet plus its own Xeno. Notice that this Higgs doublet here has the same gauge quantum number as the lepton. Okay, they have exactly the same gauge quantum number. So you could wonder whether this, sorry, here this guy is a fermion and this is a scalar. Okay, here I went the other way around. This is a fermion, this is a scalar. I wrote first the ordinary particle and not the superpartner. We could put L and H, one of the three leptons and one of the H1 in the same chiral multiplet. Okay, that would not be too good, because that when it would mean that when the Higgs acquires, so these two guys will have the same lepton number, and when the Higgs scalar acquires an expectation value, lepton number is broken, and we don't want lepton number is broken. So that's the reason for this separation of these multiplets. So this is the structure, and then you have the gauge multiplets. Okay, and then I'm done. The gauge multiplets consist of W, let me call it W alpha. Okay, the field strength superfield in the say the SU2. This is SU2. There is the W mu nu. Oh, damn it. W mu nu A, and its own gaugino alpha A, where alpha, this mu nu and alpha are the Lorentz indices. Okay, and then there is the same thing for U1 and for SU3. Okay, U1 you have the W alpha. This is B mu nu, and this is the Bino. Okay, the guy, and then you have the gluino. How can I call the gluino? I don't know. Let me call it whatever. The G alpha. Okay, this is G mu nu, and this is color, and then there is the gluino alpha. Okay, so that's the structure, and let me take. I think I started 1 minute late, but let me give you a very first hint of what goes on in this model. Okay, that is already showing something very different and just showing how things change. Okay, so at the level of d equal 4, so let me start doing the same analysis that we did in the standard model. D equal 4 means d equal 3 in the superpotential. So we have a set of chiral multiplets. Let's write the most general d equal 3 superpotential, d equal 3 or less. Let me just do it like this. Okay, and the superpotential consists of this. There is a part that is very much along what you have in the standard model. There is y up, ij, qi, h2, uj. So this is the up ucavas. There is y down, ij, qi, h1, dj. This is the down ucavas. Then you have the charged lepton ucava. And you can tolerate a mass term for the Higgses. I will discuss better tomorrow what the issue is with this mass term. Okay, this is a mass term for the Higgs, but the associated mass parameter transforms under a chiral symmetry. This is why we don't worry about naturalness. But, and this is the unpleasant novelty, at the same dimensionality level, you have operators like this: lambda 1, I, j, k, ui, dj, dk. So what's the problem with this operator, in your opinion? What symmetry does it break? Its presence is a baryon number. Okay, this guy is a baryon. So you add in the Lagrangian an operator with baryon number 1. Means that this interaction changes baryon number by 1 unit. Okay, that's okay. To make the proton decay, you need to evaluate baryon number and also lepton number, because you have to produce some lighter fermion degrees of freedom, and these are electrons and neutrinos. Okay, so this is not yet too worrisome. Okay, the proton is still there. Sure, neutrons can oscillate, but who cares if neutrons oscillate? Okay, neutron into anti-neutron, but then you can have stuff like this: lambda 2 I j k, Li, Lj, Ek, and that's it. Okay, this violates lepton number. Okay, in exactly the same way this violates lepton number by 1 unit, and you put everything together, you make the proton decay. And then you have other things to make things worse. You have lambda 3, I, j, k, qi, Li, dk. This operator exists because the lepton chiral multiplet, have the same quantum numbers as the Higgs, one of the two Higgses. So the role of the Higgs should be played by lepton. It's precisely the problem. The problem I was trying to avoid before comes back when you write the more general Lagrangian. Okay, it's not the version of all that is possible. It's compulsory, but we are getting close. And then there is another term, the similar mass term, but mixing Higgses and leptons. Okay, so that's already, and that's an incarnation of what I told you before. At the normalizable level in supersymmetry, you can get rid of all those accidental symmetries we had in the standard model Lagrangian. And now this is not nice, but it's not so bad. Okay, it's not so bad, and it can be eliminated with a little assumption. And the little assumption is the following: if you regard these two pieces, okay, these two terms, there's still a way to distinguish them. If I think of a symmetry which I call matter parity, under which all matter Q, U, D, L, E go to minus, are odd, and the Higgses, the H1 and H2 are even. Okay, consider the following parity. Okay, the following Z2 symmetry. Now the first line is invariant. Okay, because it either are quadratic terms in matter, okay, or terms that involve only Higgses. But the second line is odd. Each and every term in the second line is odd. I have 3 matter here, minus 1 cubed, minus 1, minus 1, minus 1, minus 1. Okay? And if for some reason this symmetry were to emerge accidentally in some previous slice of the standard of the standard model, then we could be in good shape. And for instance, in some grand unified theory, this arises as part of the center, like in SO10 with is part of the center. In some choice of multiplet, this is just an accidental symmetry that you get.
Is it an accidental symmetry or discrete nature?
I must have. Let me tell you, I haven't thought about this. I think it's a.
Because I mean, this is naturally embeddable at SO10. If you break
Yeah.
SO10 to Z2, it's a little better. I mean, yeah.
It's little, yeah. But you see, but you need 126, and then 126 bar, and then you basically have a gut with 250.
Yeah.
So the coupling is fixed and goes to practical infinity. The theory is already, but it could be the theory is kind of strongly coupled around the Planck the gut scale, but yeah, that's an option. And this symmetry, when combined, matter parity times -1 to twice the spin of the particle, this is what is known as R parity. So the absence of unwanted effects in baryon lepton number forces us to impose or assume there exists, either exactly or approximately or accidentally, no matter what, a Z2 symmetry which can be equivalently described by what is known as R parity. And R parity is a Z2 symmetry under which all the standard model particles are even and all the supersymmetric particles are odd. If the symmetry is exact, the lightest supersymmetric particle is stable. If it is neutral, it is a reasonably good dark matter candidate with all the limitations that Mariangela discussed the other day. Sorry, I stop here. Sorry, guys. I took advantage of your.
One last question before lunch.
Was on the other side. And now all these extra particles are on the other side or something. I hope it's not the same.
I think it's lunchtime.
The other thing is that I hope we don't get burned as we go across the horizon. That's the other thing, because at third it already happened once that they blew up everything.
About conformal technicolor.
Yes.
And so you made the assumption that this conformal